Hi and welcome. I will talk about this formula. This seems to be the best approximation for the factorial numbers. I will try to convince myself that it's true. After some search on Google, I have found these documents which talks about some approximations like these, but all of them are mentioning the best formula is the Stirling's series here. And this document says that if you evaluate the complete series, it's truly equals to n factorial. Problem is that is not true. If you, I don't know what means complete series when it's infinity, but as you approaches to infinity, this sum gets also to evaluates also to infinity, so the approximation gets worse. So here is a formula which we need to understand first. So another search now directly for the Stirling formula or Stirling series led to this document. I don't know why just the first four elements are exposed here, but in this math word or which Wolfram document we get another formula to get or to calculate these numbers, the Stirling numbers, or what are they? Coefficients. Not just the first four, but many of them. The problem is when it seems too complicated. The first formula for an to be these numbers here, 1 over 12, 1 over 288, and so on. This first formula is using another formula, this d3 of n and k, which is some permutation cycles permutation of n with k permutations. I don't know what this does mean. And if you go to the link, you get another definitions that is talking about the first order Stirling numbers and the second order. We need the third order. I don't know what order, but the D3 we need. And problem is involved from mathematical software. We don't have just the first two, the first order and the second order. We don't have the third case which we are need. So we need to use this another recursive formula for that, the dr, where r is 3, the recurrence relation. And if you can see here, this n minus 1 of r minus 1 is not some simple thing. This is the following factorial combined with some initial conditions. So if you're getting into the following factorial, again, to understand what is meaning, you can find out this is the Pochhammer symbol or who knows what, but now here we get the luck with the Wolfram language, you have the factorial power. So if I'm putting this all together in Wolfram Mathematica software, the second formula should be what we need. Here, as you can see, these are the dr. I also calculated the d3 because it's easier. My set the factorial power, especially for r equals with 3, but let us remain on the general formula. So this should be the a n numbers, and as you can see, I made the list for the for the first 4 elements, which should be the same as in the documentation. You can see it's likely the same, or should be the same somehow. Yes, it seems to be the same. And the big problem is that if you want to compute more elements, for 6 it's working, maybe for 8 it's working, but if you want to compute 10 elements, it starts to compute and thinking. Okay, it took some 10 seconds, but if you wanted 12 elements, you have to wait now. Just 12 elements, and the software is unable to calculate reasonable time. So I have to stop it. I can use even the T3. Maybe it's faster, but I think it's not. As you see, also the same thing. It's thinking and waiting. For 8 elements it's working faster. Okay, so maybe we can take another formula for computing the Stirling series coefficients. Here says another formula. It's again recursive one. First you need to calculate this Bn series or formula, and then you can use it with a double factorial. Again, you should understand what is that, but we also have luck because Mathematica knows this double factorial. So using this formula, as in here, let's try with 4. Pattern on the right side. What's its problem? Maybe I need to do an enter here. Okay. So seems to be the same results for 5, but seems to be slower. So even for 6 elements they start to hang. This is the old result, and here you can see this bold line means that it's computing. Okay, now it's finished. So even for 6 elements it's too slow. So I need to find another way, and found in this text on this page where she is talking about the same thing, and somebody mentioned this Wolfgang Hinze method to get the series. That means the Taylor series for the n factorial, which the Wolfram mathematical software can compute to you, and from there you can get the coefficients. This seems to be a better computation. So here would be the series representation. Okay, it seems too ugly. Let's try with 5 elements. Don't know why it remains here. It doesn't look so good. But anyway, we can see some coefficients here that might be good for us. But how can we extract from here? It's just if you are dividing with this function. Okay, so as you see here we have all these, the Taylor series of the x factorial or n factorial. I can change it to n. I will not. I don't know why is that true, but if Wolfgang Hintze said so, we should accept it. So the real E and Stirling series coefficients are the series coefficient of the nth term from this series. So this is the first, second, third, and so on. The good thing is in this approach we can use 80 elements. It's able to calculate 80 elements in a very fast way. It's just assigning this variable to the series and then get the nth element. And when I'm using this table, we should use 20 elements here, for example, to see how fast it is. The only time is to calculate this series first. All the others are getting very fast. So here are 20 elements. So I show this just because to know that I have to use this method for computing the Stirling coefficients here. And now that we can have all these k's, now I can test this Stirling series if it's really true that as you approach it to infinity this gets better approximation for the n factorial. And for that I will open a new document in this document of 2. In this notebook I have made these specifications. Here is the computing series for Stirling coefficient. And here is the Stirling series formula for approximation. And below is the main formula for approximating n factorial. And I also prepared a test case. The most simple value is 1. 1 factorial is 1. So we can compare in this way. All the cases. This is the best or formula with all these values should be 1. So we should check if these values is approaching to 1 or not, or how far, or which is the best approximation to 1. The first line is my formula, the second line is Stirling's formula, which in this line seems to be better, but wait a minute, not so fast. And these are the differences between the n factorial and the formulas. So the difference is 0.0, and here are 2 decimals is the approximation. And we are using these k values from the definition. This k should be the ... which approaches to infinity. So what this document is saying, that if this k approaches to infinity, this Stirling series formula approaches n factorial. And if we are using or setting this key value, this should be the key. I'm starting from 1 and ending on this special calculation or computational number plus 10 or plus 20 to see more elements, to see if it even gets better or not. So when I'm hitting the computation button, then we can test it. Comparing these results in this list can be seen that for k equals with 6, the Stirling formula is the best approximation of the number of 1. Starting from 6, so on, 7, 8, it's getting worse. As you see, the difference here is starting to fall down the decimals, and if we are going down, we can see that for k equals with 17, the Stirling formula outputs 1.14 and so on. So it's starting to be a very wrong result for that, and even worse. It's minus 0.2 and 12 for 21. It's outputs 12. And 14. So you cannot rely on the Stirling formula after the value of 6 for k. And if you compare with my formula, even after 7, it's very accurate. The difference is 5 decimal places. 10 on the power of minus 6 means that 5 decimal places is approximating. So 5 decimals is okay, and then the following are bad. And here is even better, it's 6 decimal places. 1, 2, 3, 6 zeros are here. Okay, this was the 1 factorial, it's not a big deal. We can take the 5 factorial. For 5 factorial, the result should be 120. This is 5 factorial in reality. And now this is the last value. That should be the best approximation for k equals 31. That's why I put this number here. So again, for the first values are not so accurate, but approaching to 31, it gets more better. Like you see, it's 13 decimal places, but the Stirling formula is only 11 decimal places. You can see the best formula is 2 decimal places better than the Stirling formula. And again, let's see what's happening when we are reaching 31. This is now 15 decimal places. It's 15 zeros here. Stirling formula just 12. So I have 3 decimal places more or better than the Stirling formula. And after that, if you are going down, checking, here is starting to fall down the accuracy. Is now again 14 decimal places, but if you want to be sure, I can put here to add 100, or not so fast because I have just 70 coefficients computed here. Maybe if I'm putting here 80 and can calculating. Now we can see what's happening on here and here, and for 81. As you see, the 41 is in, or the 81 is indeterminated, can't be computed. So the last one where we had is not even best. It's not even approximates the the 5 factorial. It's 1 decimal place is just. So you're not so good. So starting from 31, the situation gets worse in the Stirling formula. And even in my formula, if I'm using more than 31, it gets worse. But anyway, it's better than the Stirling's computation. So what I want to say is that the Stirling formula can compute and approximate n factorial when this key value is rounding to pi by n. And the best formula is nearly the same, just that is 2 pi by n plus 1. I computed these series coefficients until 100 terms, and we can compare here the results for n factorial from 1 to maybe 20. But as you see, for 1 factorial, the best approximation seems that with 3 decimal places is better than Stirling, and we are going on. 3 factorial, it's again with 3 decimal places better. 4, 5, 8 factorial. Starting from here is again 3 decimal places better than the Stirling formula approximation. This should be the 8 factorial. All these need to be zeros. Here just until this decimal is 0, Again, the 999 is as good as the zeros. So we can go until it's 11 factorial. Again, this is the original, and here is again 3 decimal places better. Stirling formula here gets worse. Let's see how much we can go. Okay, for 16 factorial I cannot compute the coefficient for the Stirling series, but for 15 is the last where I can, and here again is, I don't know, is too big this number to show here. These are not decimals but real numbers. Okay, but you can test it if you want to see if I'm true or if I'm true or not. This is just the real-time calculations to see in real time what's happening when you're summing these terms of the series. And now some proof here. The base idea would be the Euler-Maclaurin summation formula, which means that this sum of any function, it equals with this another sum including the Bernoulli numbers and the mth order derivative or m-1th order derivative of the function, or better saying the difference between these 2 points a plus m by x and a. Here this sum I put to be from 0, which means that m minus 1 is minus 1. The minus 1 order derivative is the antiderivative. So we need to calculate integrals here. The 0th order is the function itself. So start to plug in all, and plugging in 1 for a and x, and for the function to be the natural logarithm, we end up with these results. The antiderivative of the natural logarithm is this function. The 0th is the natural logarithm, and the others, where m is greater than 0, should be this formula. This formula also gives Mathematica 2. If I'm using the derivative function with this y variable, and for an m value, an mth order, also Mathematica gives this result for m greater than or equals with 1. So putting all together, we get this equality. Again, k and this r of n and k is the remainder term of the Euler-Maclaurin summation formula. Another technique or another good point would be to calculate. So this is the base formula, expanded formula for plugging in all the values. But doesn't help us too much until we use this n as a very big number which approaches to infinity. In that case, this sign is not infinity, just a big number here. In that case, using this Stirling formula, or better this Mortich's formula, as seen in the documentations. We can subtract these two lines and will remain this result, as you can see. So this formula can be used to compute the n factorial with high precision. Only one step I made, that I added also logarithm of n plus 1 on both sides, because in that case I can simplify better to not use n plus 1 but just simple n. So we end up with this formula, which we can use it for testing. I made a list for comparing the approximation formula. The first line is the logarithm of the n factorial. Like for n equals with 1, 1 factorial is 1, logarithm of 1 is 0. This is logarithm of 2, and this is logarithm of 3 factorial, which is 6, so logarithm of 6. The second line is the approximation, and the third line is the difference between these two. It means that this is the remainder term of the Euler-Maclaurin formula. So as you can see, for 2 factorial, the remainder is 10 on the minus 7 power, means 6 zeros. And as you get further, the power gets, or this remainder term gets closer to 0. 10 on the minus 13, 10 on the minus 15, so on. You can use more factorials. Let's see, 30 factorial. Okay, well, the problem. Okay, I fixed the problem. So now one can use 50 factorials, and maybe it's better to add more decimal places here. Okay, so as we see, on 14 factorial, the remainder term is 36 zeros. So on until, okay, it's 10 on the minus 98. Oh, 10 on the 139. Okay, so the remainder term gets closer to 0 as the n is growing factorial. And instead of proving that the remainder term approaches to 0, I will give a function directly for the remainder term, which is similar or like the same as the remainder term. And here is the remainder term, this r. It depends on n and k. And I add it to the fourth line to see what's happening. So the last two lines are The third line is the original remainder term, and this is the function which approximates the remainder term. So it can be seen that only in sign is different, so the absolute value of the remainder term is the same. But starting from n equals with 4 gets better the approximation. Now is 2 decimal places, and from 9 is 3 decimal places, 1, 4, 6, 1, 4, 6, and then on the minus 26. Okay, so this function, better saying, we can use this function as the remainder term for the Euler-Maclaurin summation formula. This is very cool. Well, I cheated a little here because the remainder term depends on k also, but I used directly the best value for k here just for comparing the values. So you might ask some questions about this remainder term, but let me show by plotting or drawing the graph of the function of the remainder and the original remainder term, how they are behaving each other. So now the variable in this graph is the k. So I'm varying the k from 1 to who knows where. Now I know that it should be 2 pi by n, but I can put here everything or anything. Just for good results, just to be able to compare. It's very trivial result for 1, but you can test for 5 factorial. Better to put here n because this is the normal values, but let's see what's happening after the best value. So plus who knows how many steps I would need to. Maybe if I'm putting 10 times n or 15 times n, okay, you are free to test it and understand better the behavior of this function remainder term. You can analyze it freely. This graphic represents the variation of the remainder depending by the key, this k value. And we are curious in which point, which is that k value when this graphic is the best approximation, where is the minimum point of this graphic. And for that we need to calculate the derivative of this function and find the point where it's 0. Software can help us to calculate the derivative of the function. Variable is k. But it looks too complicated. Maybe if you are simplifying it. a little. I don't know if it's simplified or not. Maybe it's better to use this substitution, because as you see these terms are the same except this and this, so we can use an expression for this k variable like this, and we can define another function with this y variable based on this expression. So usually if I can replace this variable with y and the k variable with this expression. Okay, this can be simplified. Pi can be extracted before the square root. I can use this, or let's try this. So instead of simplifying r, we can simplify or get the derivative of this g function by the y variable, and voila. Look at it, it's much simple. So this is a product. So the product we need to calculate when this product is 0. The product is 0 when one of its elements is 0. Y cannot be 0, and cannot be 0. This Euler number cannot be 0. So this parenthesis is the important thing. We should consider this as the resolution of for our problem. So I will try to calculate, but when this is 0, and let's say why we are interested in. Okay, so cannot solve with methods available. What if I'm setting a concrete value or fixed value and solve this value, for example, n for 6 or for 5? Cannot be solved, neither. Solve it numerically. No resolution. What else can we use then? Let us see if we have some documentation. What other functions exist to solve values? Find root, search is numerical root. Example. What's example? Find root. Have to add a function and define the variable and the point near the proposed root. Find root. Function indeterminate is not a list of 0 is a problem. Like 1. Okay. Now find root. If I'm trying to the same. 0.98. It seems that the result is 1. The root of this equation is 1, should be near 1. What if n is 7? 0.98. 8 factorial 0.99. Seems that the root of this equation is 1. So y is equals with 1. That was 100 factorial. Okay, it's near 1. So if somebody has some time, we can prove that this equation, converges to 1. The root of this equation. So this means that, as we said, k equals with 2 pi by n divided by y, and if y is 1, then k, that's right, it's y equals with 1, then k must be equals with this 2 pi by n. Surprising result. We have a result which that the graphic is the minimum point. So this is the best k where the approximation is precise and can be used. After this k value, the approximation is getting worse and we can't rely on it. One more thing, this is the remainder, the function remainder, the approximated remainder. So what's its value? Because now we have the last k value, but we also have a remainder which can improve the approximation if we are plugging in 2 pi by n instead of k. So how much is this value of the function? Yes, not okay, can't set n here. I'm deleting all this. Let's see. So this is the remainder term of the Euler-Maclaurin summation formula for the natural logarithm 1 over this. So if I'm going back to our previous document here, and here is the remainder term, and now instead of this function I will use directly that value, the best approximated value from here. Let's see what will happen, how it compares with the original or the other Okay. So this is the let's see, where is that? The original remainder, the function approximated remainder, and now these two, who knows what, square root pi and else. Surprisingly, for short values or small values, it's best approximation by the original, not the function remainder. And going further, it's worst for 5. For 6, let's see, for bigger values, 11, but it seems that approximately the same. So it can be used to improve the results. 286, 286. Let's see for bigger numbers. I can say that we can use this approximation. Here's even better. 987, 986 the original, is 995 the function. Interesting. But the conclusion is that this is the remainder term of the formula. Such a beautiful formula. And finally, I made again a test with this new result, including this such a beautiful formula. The difference is that I plugged in n+1 instead of n. And because of the absolute value, because of the sign of -1 or +1, I found that this expression could reflect better the truth. This is the complex unities, square root of -1 on this power. So usually if I'm using even values as the power, this is -1 or +1, but on odd values this could be complex numbers, and even in this case I need some real values to use. But putting all together, I made this test, and seems that here I use the best formula. The best 2 is with the remainder term, and the best 3 is with such a beautiful formula as the remainder term. So we can see the results slightly the same or better for this new formula, or this new case. Can check, for example, 4 factorial is formula is from here, and the best 2, including the remainder term, is even better with 1 decimal places. And this is that pi formula. It's nearly the same. Can check some late how much is. For 7 factorial, best formula is the same, but it's better than the best formula. So here is 2 more decimal places added for precision. It's the precise calculation, precision. So the final conclusion that the even better approximation method for the n factorials should be this formula, where the sign is plus or minus 1. That is a correct calculation or how to get that plus or minus 1 value. It's really surprising, isn't it?